In this lesson, we will discuss how the output or terminal voltage of a DC generator or an alternator is maintained constant, in spite of variations in the load current and the drive speed. We will also look at how an electrical system's redundancy can be improved by operating DC generators in parallel. Most light aircraft DC electrical systems operate at 14 volts, and so all the equipment is designed to operate correctly when supplied with 14 volts. Larger aircraft DC systems operate at 28 volts. It is necessary for the output of the generator or alternator to be controlled or regulated, to ensure that at all times the output voltage is constant. The output voltage of a generator or alternator is dependent upon the number, size and shape of the armature windings, the speed of rotation of the armature or field, the size of the load being applied, and the strength of the magnetic field. Of these factors, the number, size and shape of the turns are design factors, and therefore the operator cannot alter them. The generator or alternator is driven by the engine using a drive belt or directly from the engine accessory gearbox, and therefore the speed of rotation of the armature or field is linked to the speed of rotation of the engine. Controlling the output voltage by controlling the speed of the engine is not normally a practical solution. In fact, it is necessary to maintain a constant voltage in spite of changes in engine speed. The only practical method of controlling the output voltage of a DC generator or an alternator is to control the strength of its magnetic field by controlling the current flow in the shunt field coil wound around the magnetic pole pieces of the field magnet. Control of this current flow is achieved by use of a voltage regulator, which places a variable resistor in series with the shunt field coils. In modern voltage regulators, the resistor is controlled by an electronic solid-state system. In older voltage regulators, the resistance in the field circuit is controlled electromechanically. The most common electromechanical system is the carbon pile voltage regulator. A carbon pile voltage regulator uses a carbon pile as a variable resistor. The carbon pile is a stack of carbon discs, whose overall resistance is inversely proportional to the amount of compression of the stack. The more the stack is compressed and the discs are pressed together, the lower is its resistance. And the less it is compressed, the higher is its resistance. The carbon pile is held in compression by spring strips. Pushing on the soft iron base plate at the bottom of the pile. The carbon pile is connected in series with the generator shunt field coil. Mounted below the carbon pile, there is an electromagnet, the coil of which is known as the control coil. The control coil is connected in parallel with the generator armature and the field coil, so it is monitoring the generator output. The magnetic field of the control coil attracts the base of the carbon pile, and the stronger the magnetic field, the greater is the attraction. This attraction is being opposed by the springs, pushing the pile in the opposite direction. Because the control coil has a fixed resistance, and Ohm's law states that voltage equals current multiplied by resistance, the current through the control coil will vary in direct proportion to the generator output voltage. As the current varies, so will the strength of the magnetic field produced by the control coil. The regulator is set up so that at the correct generator output voltage, the spring and the magnetic field of the control coil are balanced. If the generator output voltage increases above its regulated value, possibly because the engine is accelerated, then the control coil current will increase, increasing the strength of its magnetic field. The carbon pile will become less compressed, and its resistance will increase. This will reduce the current flowing in the field, and the output voltage will fall back to its normal value. Similarly, if the generator output voltage decreases, the carbon pile will become more compressed, and its resistance will decrease. This will allow an increase in field current, bringing the output voltage back to normal. A twin-engine aircraft will normally have a generator or alternator driven by each engine. In some systems, both generators feed the same busbar. This is known as paralleling generators. Each generator is connected to the busbar by its generator control breaker. The generator control breaker is a large solenoid-operated switch, which enables the generator to be connected to the busbar when its voltage output is correct. It may be controlled automatically or manually by the pilot. The advantages of operating generators in parallel are that it allows the generators to share the total electrical load of the aircraft, and it enables power to be maintained in the event of a generator failure. When operating generators in parallel, it is necessary for each generator to supply half of the total current demanded by the loads on the busbar. This is known as load sharing. To achieve load sharing, the output voltage of each generator must be exactly the same. If there is any difference in the voltage between the generator outputs, then the generator with the higher voltage will supply all of the loads. And in systems using DC generators, current will flow from the generator with the higher voltage into that with the lower. This is known as a recirculating current. The current flowing to the low voltage generator can be very high, and it will be attempting to turn the generator into a motor. The attempted direction of rotation of the motor will be in opposition to the direction of rotation of the engine. This flow of current is undesirable, and parallel systems using DC generators have reverse current relays fitted to protect the system in the event of a failure of the load sharing circuit. The load sharing or equalizing circuit monitors the output voltage of each generator. If there is a difference between the generator output voltages, the load sharing circuit will send a signal to the voltage regulator of the high voltage generator to reduce its field current and thus its output voltage, and a signal to the voltage regulator of the low voltage generator to increase its field current and output voltage. The two voltages will come together, and the load sharing circuit will then keep them equal. That is the end of the lesson. You now know that the output voltage of a DC generator or an alternator is maintained constant during load and drive speed changes by a voltage regulator, controlling a variable resistor in series with the shunt field coil. You also know that in parallel generator systems, the load sharing or equalizing circuit keeps both generator voltages equal by sending signals to the individual voltage regulators. This ensures that each generator takes an equal share of the applied load.